Hello, this is another INB382 demo where we're going to have a look at the Ashikhmin Shirley shader. Try and say that 10 times very fast. So as we can see here, I'm just in Unity and running the shader, and it's not particularly amazing, but there are some factors in it that are an interesting sort of interim between our standard Phong shading and lighting model and more physically based modelling that will be done later in semester and in this lecture with BRDS. So there's a number of things to note here. First of all, have a look at the specular component of this lighting model here. You note that it's asymmetric or asymptotic, not asymptotic, anisotropic. This means that it does not have physical properties that are equal in all dimensions, and so we end up with this sort of lobed appearance to the specular components of the lighting. And that means that we have a bit more control over its appearance, and we can sort of get some interesting effects, as you see down in the corner here. Because of this anisotropy, when we move the geometry around, we get some just bizarre effects with the specular component. And this happens in real life when you look at objects that have surface properties that are anisotropic, such as satin, brushed metal, hair, all sorts of things that tend to, I guess, have a dominant dimension in their reflectance for specularity. And if you're going to model that, you need to model it in your code. So without further ado, just moving to the shader code here, and we see that, so this is converted from a shader I found in Programming Vertex and Pixel Shaders by Wolfgang Ungel. And we have sort of typical parameters here. We've got a light position and an eye position for the specular components. So, you know, that's fairly straightforward. But here we have our mx and our my, which are terms in the theory that I cover in the lectures that control this anisotropic component of the specularity. So those properties are used down here. So first of all, we move to the vertex shader, and there's a number of things to note. First of all, this is where we start to use the tangent basis system, or the tangent basis vectors across the surface of objects in order to determine at an object surface local manner lighting effects. Now, we'll see this in normal mapping, but this is where it starts to be used. And first of all, just to point out here, so we have the position coming through, the usual transform by the Unity matrix MVP. Then there is the normal, which we do the usual inverse transpose transform in order to preserve its orthogonality to the surface. But as well, we have a tangent. And the tangent is passed in from the mesh. And I cover in lectures that Unity is able to generate tangents across the surface. Watch it. It doesn't do it perfectly. So hopefully a tangent for your binormal system will come in automatically with the mesh, but Unity can generate them for you. So the tangent comes in and we transform it with the object to world because we do our calculations in world space. We don't project it. So note this is a world space tangent, same with the normal. And we then have to generate our binormal. So remember, the orthogonal space on the surface is made up of a tangent, binormal, and normal. So we get the normal and the tangent. We have to generate the binormal. And to do that, we simply do a cross product of the normal with the tangent. And lo and behold, we end up with a binormal. And that completes our orthogonal coordinate system on the surface of the object in order to enable us to do our lighting calculations in that orthonormal space on the surface. And this is managed by a trick, GPU programming. We have limited resources in shader level 3 CG shaders for sending parameters out. So remember those semantics that I told you that generally map to fairly logical concepts like the position of the object, and so forth and so on. Well, the semantics, to a certain extent, are arbitrary. You can use them to line up variables, but they don't actually mean anything to the shaders. So here we can see that, all right, the output, what comes in is the position, what goes out is the system value position, because we're passing it along to a geometry shader, or more likely a pixel shader. But as well, we want to send things such as the viewpoint, the light position, normal, tangent, binormal. We can pass these along in texture coordinate semantics, which is interesting because we could pass out the normal as a normal, but because I swiped this code, quite open about it, from a textbook, they used initially the semantics, these texture coordinate semantics, in order to pass these values out. So keep this in mind, that when you're looking at a shader and you go, hang on a minute, it's normal, and it's been passed out as a texture coordinate, you can do that as long as the input matches for the pixel shader. So we see here that texture coordinate 2 semantic lines up in the pixel shader with the normal here. This is important, and that means that it will work. So keep that in mind when you're trawling through shaders, that sometimes these semantics do not have to match the variables. It's actually bad programming. It's obfuscating. But I guess I haven't modified it. And it just illustrates this one of those side effects of a language like CG. Moving right along. Here's our pixel shader where all the magic happens. So once we've got our orthonormal bases set up in the vertex shader, we now move, of course, to the pixel shader where we implement that quite complex components of the Ashikhmin lighting model. And what we see here is that it sets itself up with, okay, normalizes the normal, normalizes the tangent, normalizes the binormal, sets itself up with also normalized light and view vectors, calculates a halfway vector between the light and the viewing point, which matches Blin's model of lighting. It's a bit of a modified version of Phong lighting. But as well, we've got some dot products that are automatically calculated here, NV, NL, NH, so forth, T1H, T2H. These are used to calculate our diffuse specular components, and then these are all munged together to formulate our final expression, which comes out down here. Now note, there's a lot here. So first of all, the diffuse component, RD, is made up of this function here. And we note it's just a more complex Fresnel based version of the Phong shading, so that's okay. The other trick then is that we need to do some subcomponents for the specular here. So calculating the specular, we've got to do B, which is this here. It's just a long expression based upon the modeling that's been done, and I'll talk about it in the lecture. But note the 2 factors here that matter, mx and my. Mx and my are what control this anisotropy of the specular component. And then the rest of it, f, this function here, a, this function here, which again contains the mx and the my. Multiply them all together, you get a specular component. Now, as per sort of standard lighting models, so, you know, the diffuse and specular, that's all done for us. And then we come back down to, all right, here's the final lit value for the surface, which is, you know, an n dot L modified by this term, which gives us some of these properties. And we see here that the diffuse and the specular are multiplied together by their appropriate KD and KS terms, which represent the reflectance of the surface, as we can see up here. It's defined like any other normal Phong shading. So the reason for this, and the reason why I put this into the unit, is just to show that, okay, you've been taught Phong shading, and this is, you know, what people say is real-time shading. Okay, that's the first step. But if you want more subtle effects, you have to start to model more factors, and this means that you have to have much more complex models. Take that as a given for the purposes of this unit, and just understand that if you're going to try and model some of the effects of light across the surface of an object, you have to do some very complex modeling mathematically. And yeah, you should do a physics degree or an engineering degree if you want to do that. For us though, we can play with just some of the parameters to get a feel for how this works. And so we're going to take the mx and the my and we're going to play around with them across the surface. So the others are fairly straightforward. There's a diffuse and a specular component values that we can use to reflect various intensities. So they've all been sort of set up appropriately. And what we get is, this appearance. Now, it sort of looks like it's diffuse, but it's a different sort of diffuse effect. As you note, the fall off is very different on the surface. But the key component is that you can add this anisotropy to the specular. So what I'm going to do is I'm going to play around with those values. So at the moment you can see that mx is equal to 1000, my is equal to 50. As far as I know, these are arbitrary factors that you can then modify to suit. So if I set the mx to 50 on the surface, actually no, I've done that wrong. I want to do this instance. Thank you. So set that to 50, and lo and behold, we end up with an asymmetric and fairly non-specular. It's still, you have a specular component, but it's a bit fuzzy and diffuse looking. So this suits surfaces, I guess, that have a lot of microstructure that still reflect a specular component. I mean, surface properties of objects are very complex to model. So this is just a custom shader to do this, and we get this effect. And note, all that anisotropy has gone from the surface. So when I move the sphere around, it just looks like a standard, starts to look like a standard form appearance. But note, it's a more subtle, diffuse effect. So if I increase those factors, of course, you'll end up with a sharper fall off. So if I make them equal to each other, we get a much sharper fall off, and we end up with something that looks much more reflective. So this is starting to look like the sort of billiard balls I've been showing you in the lectures from the Phong shading and Phong lighting. So the trick then is, if we want to make it have an anisotropic specular property, you just make them unequal to each other. So if I make that 50 in y, we suddenly end up with the specular lobe moving around. And if as you can see, when I move the sphere, as I showed before, it deforms with respect to the surface tangent bases on the sphere. So you can imagine, of course, that the sphere is generated with u and v coordinates in a series of rings, and so we've made it that it spreads further across the x-axis than it does across the y-axis, and so we end up with this sort of lobe effect. Now, so we can play with those figures if we wish. So I guess I could probably push that up to 10,000, and we end up with this strongly anisotropic effect, which sort of just, I guess it approximates that it's strongly brushed along that direction, but not up and down. So the light is guided, so to speak, I think that would be an appropriate term, along those lines and not reflected much across the axis. So that's just the Ashikhmin-Shirley shader, and this starts to bring in some more complex components of modeling light across the surface via its sort of non-trivial diffuse effects, which start to approximate maybe pottery style things, but also more obviously this anisotropy across the surface, so that you're able to control the effects of the lobes for the specular component, which are not necessarily equal in dimensionality across objects. And that's the end of the video. Thank you very much.